Hello guys, in today's video we're gonna be talking about one of the most important, if not the most important machine learning paper in the last century. Attention is all you need. So this paper really revolutionized AI. Not only did it give us the GPT model later on, it inspired it, which gave us ChatGPT. It also gave us the VIT model later on, which we're gonna be diving into in future videos that gave us later video generation, image generation. So this paper, which is I wanna say recent because it came out in 2017, so it's only 8 years ago, but 8 years in AI nowadays is a lot. So from a year till the next year, you'll see a huge jump, not only in performance but also in the results. But anyway, without further ado, let's get started. So in today's video, we're gonna be reading the paper, explaining everything written in it. And in a future video, stay tuned, we're gonna be making our own mini GPT model. So we're gonna make a small chat GPT, if you wanna say. Um, and but before we reach that video, we first have to understand how attention works and the transformer architecture. So in the abstract, they say that they propose a simple network architecture based on attention that removes recurrence, like in recurrent neural networks, and convolution. So it's solely based on an encoder, decoder, and on attention, which we're gonna explain right away. So, in the introduction, they say that recurrent neural networks they were the state of the art when you wanna work in sequence modeling. So when you have a sequence in your input, it you like before 2017, the way they used to approach it, not with a fully connected neural network. Most of the times, it was recurrent neural networks, which we're gonna be uh, briefly explaining in a bit, but they had their problems. So, recurrent neural networks, they have a so they're basically recurrent. So they have like a connection between one output and the input before it. For example, over here we have a recurrent neural network. So here we have the first word. It's injected to a neural network over here. It gives us the word 2. Then word 2 is given as context to the next level, as well as the output of H1. Then we get word 3, and then word 3 is given as context to H3 alongside H2, and we get word 4, and so on. So like, for example, um, here it may be high, so we inject it to H1, which is like a neural network, one layered neural network. We get my, and then my is injected to H2 alongside the output of H1. We get here name. We do the same process. Is, I don't know, Abdullah here. Um, so this is what was used in sequence modeling before attention came. It suffered from a few problems. The first is the exploding and vanishing gradient. So first, before we dive into it, if you're familiar with the chain rule is that if you have a function that depends on a variable that depends on another variable, to do a derivative of this function with respect to you, the second variable, you have to derive this function with respect to x, the variable that makes it, and then derive x with respect to you. Like, let's take a very tiny example. Let's say f is equal to 2x, and x is equal to u square. So to do del f by del u, the derivative of f with respect to u, which describes how much change affects f when we change u, we apply the formula. So it's del f by del x, the derivative of f with respect to x is 2, multiplied by del x by del u, which is 2u. So we get 4u. So this is the chain rule. Now, in neural networks, we apply it a lot. So let's take this input neural network I drew over here. This very simple neural network. Here we have the input, one hidden layer, and the output. And let's say that the activation, so as you may know, is that at a certain node, let's say here, we get O1, it's a hidden layer, let's call it H1. So H1 is equal to summation of Wi xi plus bi, but after we do this process, we do our activation function. So let me delete. So it's the activation function of summation Wi xi plus bi. So for example, here we at this layer, it's we have just one connection to it, which is the first input. We get and let's say here we have W1. We do W1 multiplied by X1. We add B1. Then we do the activation function. And in the example over here, I put the activation function in the hidden layer is the maximum between 0 and X. And then after we calculate H1 and H2 and H3, what we would do after is that to calculate the output, we do output is equal to summation Hi Wi plus Bi, as I explained just now, and we apply the activation function of the output layer. So we do activation of summation Wix, the Hi Wi plus Bi. And the activation output of the output layer here is activation of x is equal to x, so it's the identity. So if we give it 2, it will output 2. Here, when we want to do gradient updates to W1, as you can see, so we, as you know, in gradient descent, the way we update to weights is as follow. We do WE1, so the new weight is the old weight minus alpha, the learning rate, multiplied by the gradient, the derivative, of the loss function with respect to the old weight. So we have our neural network, we run an input, we get an output, and after we get our output, we calculate the loss, because as you know, we have an input, output, and we have a loss. So after we calculate the loss, we have to update W1, we have to calculate the derivative of the loss function with respect to W1. And W1 and the loss doesn't depend on W1, it depends on H1. So we apply chain rule, so we get derivative of loss with respect to H1 multiplied by the derivative of H1 with respect to W1. Now, if you have a very deep neural network, so for example, this one. So as you can see, you have many layers. So here we have the output, here is the output, and here, let's say you have W1. How many layers do you have in between? 1, 2, 3, 4, 5, 6, 7. So you have around 7 layers. So you're doing a very long chain rule. Let's say here you got 0.1, and here in the derivative, and here you also got 0.1. 0.1 multiplied by 0.1 is 0.01. If you imagine a very deep network, once you get here, if you have very small gradients at each layer, you'll get 0.1 power 7, for example, if you got 0.1 at each gradient. So when you apply chain rule and you reach this level over here, you'll get 0.1 power 7, which is almost 0. So you got almost 0. You want to update. So you want to update W1. You put W1 new is W1 old minus learning rate multiplied by the gradient. And here you got 0.1 power 7. It's almost W1. So the weight didn't get updated. And because the weight didn't get updated, I mean, it almost slightly got updated. The network will take a really, really long time to converge. Another problem, so this is the vanishing gradient problem. Another problem is the exploding gradient problem, which we would get if we got a very big derivative here. So let's say here we got a big value for our gradient. Let's say we got 7, here we got 6, here we got 10. When we do a very long chain rule, we will get a very big number when we want to update W1 prime, which will make it diverge from its optimal value. So here I have a curve for the chain rule, not for the gradient descent, and we want to get the optimal W. If we have a vanishing gradient, the update will be very, very, very minimal, which will make the network take forever to converge. While if we get a very big number, we will jump from here to here. So it will also be very hard for the network to converge. And this is one of the main problems recurrent neural networks suffered from. So in the past, if you went to Google Translate and you gave it a very big paragraph to translate, it gave a rubbish output. And the problem was that if you wanna translate a paragraph of 50 words, as you can see here in a recurrent neural network, over here, if you wanted 50 words, you needed 50 H, and so you had a very deep network. So if you got you wanted to translate 50 words, you needed a very, very deep network of 50 H. So here you had H50, for example. And because the network was so deep, the output, it wasn't trained enough. And because no matter how much you trained it, it will it will converge, but is it worth it? So the output of Google Translate, for example, at 2017 was rubbish. And the main reason was that it couldn't handle very long sequences. But if you gave it like a tiny sentence of 10 words, it would translate it because the network isn't too deep. So vanishing gradient in their GPUs of Google, the vanishing gradient didn't suffer as much. Mainly vanishing gradient, exploding gradient. And recurrent neural networks not converging for very long sequences. And here attention came to play to solve this problem. So now let's continue. Now for the background part, you're free to read it, but I'm gonna skip it for now. For the architecture, this is the architecture of the transformer. This is what inspired the GPT model later and gave us ChatGPT, and even inspired video generation later on. It looks complicated, but believe me, it's not. I'm gonna be explaining every part of it alone, and then we'll see an overview of the architecture later on. So first, attention. So attention is this part over here. So attention, as described in the paper, it's a function that, given a query and given a key and given a value, it gives us the output. And from my understanding of of attention gives us like a matrix, and this matrix would give us the relationship between every word and every other word in a sentence. So, for example, if we have over here, I am Ali, I go to school, it will give us a matrix of size. So here we have 1, 2, 3, 4, 5, 6, 7, 7 by 7. And for example, I would A11, the first element of the matrix, would give us the relationship between I and itself. For example, here it will be a very large number, 0.8. Yeah, and the numbers are between 0 and 1. Whereas if we take I and school, they aren't very like correlated. So if we take I and school, we would get a very low number, for example 0.1. But if we take I and Ali, so this one and this one, we would get a very large number as well, because if you understand the sentence, Ali is speaking about himself. He uses I to describe himself. So A13 or A31 in this case would be, I don't know, around 0.7, for example. And I and am also are kind of correlated, so it's like 0.6. I and I, not so much. I and go, you get the idea. So you'll get a 7 by 7 matrix giving you numbers between 0 and 1, describing the relationship of every word and the other words of the paragraph, because you may have a paragraph of size 100, so you have 100 words, you'll have a matrix of size 100 by 100. I made a small numerical example. Let me paste it over here. So, in this example, I gave like how as I said earlier, we have a query, a key and a value, and how they're computed, and then later on used to get our matrix. So, first we have an input sentence. For example, I am Ali. So I am and Ali. So first we do vectorization. Vectorization, I'll explain it later, but you'll get a matrix X which basically describes the paragraph that we have. So for example, let's say I is 101, this vector, am is 011, and Ali is 110, the last column, and the middle column is am. We first calculate the query. So to get the query Q, we multiply X by a projection matrix WQ, which would, as you can see, WQ is a matrix. When you multiply it by a sentence, you will get the query of this sentence. So as you can see, WQ is learned by the network. So it's a neural network. And in the gradient descent, it's updated. So let's say, for example, we got after training our model, we got this matrix over here. Same for WK. WK is a neural network learned by our model and via gradient descent. And it basically gives us a key. So WK, when multiplied by X, gives us a key. Let's say we got this WK. Same for WV. It's a neural network that gives, when multiplied by our paragraph, gives us the value. Let's say we got this WV. So we calculate Q as XWQ. Let's say we got this matrix. This is our query. This is our key. And this is our value. So this is first step. Let me now erase. So after we, so the formula is over here. We calculate the query, the key, and the value. Then we calculate S, which is the query multiplied by the transpose of the key divided by radical decay. And radical decay is basically decay is like the size of your vector. So here, in my numerical example, I calculated query multiplied by transpose of k. Then here, the size of, so every word got a length of 3. So d is equal to 3. So you divide by radical 3, and s is equal to query multiplied by transpose of k over radical 3. You got your s. This is the second step. The final step is a is equal to softmax over s. So you have your s matrix. You do a softmax activation function. I did it numerically over here, calculated the softmax. And yeah, that's it. After you got your a, to get your output, you multiply this a, which is the softmax of s, you multiply it by the value, and voila, here you have your attention matrix. So very quickly, I will go over it again. You need to calculate the query, the key, and the value to apply the formula in the formula over here, the attention formula. Softmax of query multiplied by transpose of key over radical, the size of your vector, multiplied by value. And you do a softmax of the first part, then you multiply by value. To get the query, you do query to do the query, you do query is equal to x multiplied by WQ, which is a neural network again. You also calculate the key, you calculate the value, you calculate s as q transpose of k over radical d. Then you multiply whatever, you do a softmax, you multiply by v, and you get your attention matrix. And the attention matrix, I mean, here the numbers don't make really much sense because they should be between 0 and 1. But this would give you the relationship. So the original sentence was, I am Ali. This would give you the relationship between I and itself, here between I and am, and here between I and Ali, and so on. Okay, so this is the attention mechanism, and again, it gives you the relationship between every word and every word in the sentence. This is the first part of our network. Now, for the later part, as you can see, here it doesn't say attention, it says multi-head attention. So what is multi-head attention? You can think of like attention is giving you the relationship between different words, right? Multi-head attention is like the model is looking at different relationships between the words. For example, let's say you have two sentences. One of the attentions would be looking at the relationship positionally. Like, for example, I am Ali, I go to school. I and I are in the same position. They are in different sentences, but as I said earlier, attention is done on a whole paragraph. So I am Ali, I go to school. I and I are in the same position, so it should give a high value. While I and school are very far apart, so their attention value would be lower. So one attention could be looking positionally. Another attention may be looking at which is a verb, which is a subject, which is the object of a sentence. And another one may be looking at references. For example, I and Ali are referencing each other in the example I gave. So if you want your model to do different views on your paragraph, like different types of relationships, you do multi-headed attention. And as they explain it here, instead of doing one single attention with the model, and so D model, as I said at the beginning, we have a word, we vectorize it, and we give it so we describe it as a vector, and the vector is of size D model. Now in their paper they gave D model equal 512, so they had 512 numbers in this vector describing every word. So for example, if we had I, I was described by 512 numbers. For example, 1.1, 0.9, I don't know. And I will get into vectorization later. Instead of doing, instead of using D model, they projected to DK and DV dimensions. So, for example, they did in their paper, they say over here, we did H equal 8, so we did 8 different types of attention, 8 parallel attention layers, and as so on. They went from 512 to 512 over 8, which is 64. So they went from 512 to 64. So the way it would be done is that instead of doing like just one attention, you would do 8 attentions in parallel. So the way it would be done is that instead of doing so as I explained earlier, we calculate the query, the key, and the value. Instead of using a size of 512 in these projections, we would use a smaller size, for example 64, and at the end, after we calculate head 1 till head h, where head 1 is like the attention matrix, we concatenate them, and yeah, that's how it's done. So here I put a tiny numerical example over my whiteboard. So let's say we also have I am Ali, but let's say instead of before we had 3 by 3, let's say we had 3 by 4. So every word is described by a vector of size 4. And let's say we wanted to so in the original paper it's 512, here we have 4, and also in the original paper they divided it by 8, so they got 64 at every in their projection. Here I'm dividing it by 2, so I should be getting dk and dv equal to 2. So as before, we calculate the query, the key, and the value. However, so here we and then just like before, we calculate S, and we calculate the attention A as the softmax of S, and then we get the output as A multiplied by A of I multiplied by V of I. So let's say we got WQ, and WQ is, as I said, 2 matrices. So the first one is over here, and the second one is over here. WK the same, and it's a these are 2 neural networks, like 2 neural networks learned by the model. Same for WV, 2 matrices, and then we get Q is equal to XWQ, which is like 2 axes concatenated. Same for key, same for value, and so I already said this. So this is Q1, K1, V1, Q2, K2, V2. The 2 different attentions going on. Then we calculate S1. We do a softmax, and we get O1, and the first output. So this is the first attention. Let's say this attention gives you the relationship of subject and verb and object. I don't know. We do the same for A2, and we get O2. Then we concatenate the 2 outputs. And this is the way it's done in the paper. Just a side note, if you're applying for a large language model internship or job, he may ask you, explain to me what multi-headed attention is, and why it's done. So for what it is, it's basically doing projections into different spaces of lower dimensions. So we go from 512, for example, to 64. So we get 8 different attention matrices. Each one of these attentions attends to different relationships between the words. And why it's done, it has been shown that the model learns better this way. So that's how you answer it in an interview. Um, so this is the multi-headed attention. We have different parts as well. We have the positional encoding now. And so now we reach the part of positional encoding. Now, before we talk about positional encoding, we should first dive into vectorization and how it happens. So, as you may all know, a neural network deals with numbers, not with characters or words, but our input is a sequence of words. So, first of all, we need to transform our sequence of words, our paragraph, into vectors. Okay, so it's the first step. Um, so I made this tiny notebook over here about vectorization and how it happens. So, simply speaking, we have a sentence. Let's say I am Ali. Okay. So first we give each word an index. For example, this gets index 2, this gets index 3, and this gets index 4. Okay. Usually index 1 is start of sentence, which is like nothing. It's called it's like a special words that doesn't exist that indicates that our paragraph just started. So we give each word an index starting from 2 and so on. Maybe we have a longer sentence, we'll have more indices. Then, after we get I am Ali, we transform each index into a one-hot encoding. So, this is I am Ali. We should be having like an English dictionary which contains all the words. So, the boy, I don't know. So all the words in the English dictionary, and at some point we get I, at some point we get am, and at some point we get Ali. Okay? So let's say our dictionary is of size 10,000. Okay? We should get where I is in the dictionary. Let's say it's at position 100. Then we represent it by a vector of zeros everywhere, then 100, then zeros everywhere. Okay? The same for am. Let's say it's at position, sorry, here not 100, here just 1. Okay? And this is called one hot encoding. And this is at position 100. Okay? And here we have 99 zeros. And here we have 9,900 zeros. We do the same for am. Let's say am, so this is for I. Let's say am is at position 200. Then we'll have zeros everywhere. Then a 1 after 200 indices. And then 9,800 zeros. Okay? We do the same for Ali. After we get our one hot encoded vectors as well as the position, so this is what I said over here. So we map each token, the token is a word, to an ID. So I gets 2, Am gets 3, Ali gets 4. Okay? And then we do a one hot encoding that I just described over now. Then we pass them to a neural network. Okay, so here we have a learnable neural network, which would be updated in our training. We pass this one hot encoded vector, let's say I, which, as we said just now, is 0, 0, 0, 1 at position 100, then zeros everywhere. We pass it to a neural network, and this learnable neural network would output a vector, okay? So it would output a vector of size 512, in this case, as explained in the paper. We do the same for we do the same for Ali. So this is what I just explained over here in the embedding trainable table. So this embedding is a neural network that's learned, and for example, I would get this, like after passing it by the neural network, would get this vector. Would get this vector, and Ali would get this vector. You'll say to me, you just said that it's of size 512. In this example that I put over here, I put the size at 4, okay? But in the original paper, it's 512. So again, we have our input sentence or paragraph. We give each position an ID. Then we have our English dictionary. We look up where I is, where am is, and where Ali is. And then we pass them by a neural network and we get our vector, okay? The next step, okay, so why did you, you said we look up in the English dictionary and then you pass by a fully connected neural network. Then why did you get the index in the sentence? It's actually to give the neural network, our transformer, to give it an idea about where the word is in the sentence. So we have a sentence. We want to know let's say we want to know that I is at the beginning of the sentence, because he should, as a contextually, he should understand where the word is when dealing with it. So to do it, as I explained just now, we have to add the position. One idea may be to just add the position as it is. So I has the position 2. So it may be to add 2 here, okay? However, it's not the best way to do it. The best way to do it is to use positional embedding, which I will explain just now. So for now, just consider that we got our positional embedding, which is another vector. We add our, let's say it's this one over here. So we add it to our word, and yeah, that's it. So the first word I, we get x of I is a vector representing I, plus positional embedding of 0, which is a vector describing 0. I'll explain it right after. We get our vector. Then so this is for I. We do the same. We get x of just as I explained just now, by passing by a neural network. Then we add the positional embedding that says I am at index 1. And Ali, we do the same. We get x of Ali plus positional embedding of position 2. And that's it. We got our X matrix that after we got it, we get the key and query and value as I explained before. However, how do we get the positional embedding? Okay, so I do know that I is at position 0, is at position 1, and Ali is at position 2. How do I get the vector that should be added? And as you can see, positional embedding is of the same size. So in the original paper, they had size 512. Positional embedding should be of size 512. So I explained it over here. They use sinusoidal positional encoding. And the way the sinusoidal positional encoding works is as follows. So we have 512 indices in the original paper, right? Divided by 2, you get 256. So you will have 256 sine values and 256 cosine values. Now, in the example I put over here, I didn't take d model equal 512. I just took d model is equal to 4. So because d model is equal to 4 in my example over here, so every word is represented by a vector of size 4, we would get 2 indices, 0 and 1, okay? So in original papers, they had 256, ranging from 0 to 255. In my example over here, I took 4. 4 over 2 is 2. So I had 2. So I took 0 and 1. Okay? So the formula is over here. The positional embedding of a position, and as I just said, we have many values. So for an index I, for a position pose, it's sine pose over 10,000. Okay, trust me, it's not complicated. It'll become clearer in a second. It's sine position over 10,000 power 2i over d model, and it's also position for 2i plus 1, which is the odd position, cosine pose over 1000 power 2i over d model. Okay? Now, for example, let's take the size of every vector as 4. Again, in the original paper, it's 512. So let's say it's 4. And the same sequence, I am Ali. Here, as I just explained, because it's 4, you divide 4 by 2, you get 2. So you have two indices, 0 and 1. Okay? So for dimension 0, 0 is you take the even numbers. So you take 2i for I equals 0 and 1. For I equals 0 and 1, you get 0 and 2. So your values, PE, would be into pose and 0, and the second time, PE of pose and 2. So for dimension 0, you get sine position over 10,000 power 0, which is 1. So you get sine position. And for dimension 2, you get sine position over 10,000 power 2 over 4, which is half, which is radical. So radical 10,000 is 100. Now, for so again, I belongs to 0 and 1. And we should be getting 2i for two values of I, which are 0 and 2. And 2i plus 1, the odd values, for I between 0 and 1, getting 1 and 3. When I equal 0, we get 1. When I equal 1, we get 3. So for dimension 1, which is odd, so we use the cosine, we get cosine position over 10,000 power 0, which is cosine position. And for dimension 3, we get cosine position over 10,000 power 2 over 4, which is cosine position over 100. Now, okay, now we got our function of positional embedding. Every vector would get these values. It would get so sine position, and then cosine position, and after it sine position over 100, and after it cosine position over 100. So this is a positional embedding vector. Now we just substitute the positions. Here we have 3 positions. We have 0, 1, and 2. When position equal to 0, you get 0, 1, 0. Just substitute 0 over here. Sine 0, cosine 0, here over 100. Sine 0 and cosine 0. So we get 0, 1, 0, 1. For position is equal to 1, sine 1, cosine 1, sine 1 over 100, which is sine 0.01, and cosine 0 over 1, cosine 1 over 100, which is cosine 0.01. We get this vector over here. The same for position 2. And finally, the positional embedding vector is this vector. And after it, let's say our x from what I just explained just now, which we get from a fully connected neural network, is this. You add the positional encoding to x, and you get your final vector. I'm gonna go over it again to make it clearer. So again, this is the formula, and also this one over here. Let's say we have I go to school. Okay? So here we have 0, 1, 2, and 3. So this is the position, okay? And after it, let's say the size of my length of vector is d equal 4. Again, in the original paper, it's 512. D equal 4. You divide it by 2, you get 2. So I would take two values, 0 and 1. Okay? If it's like in the original paper, 512 over 2 is 256, so it will go from 0 to 255. First, you get sine pos over 10,000 2i over d model for the even, and when you use 2i plus 1 for your two i's, you use the cosine. So in this case, so again we have 0 and 1, so we would be doing it for 0 and 2 for even, and 1 and 3 for odd. This is for the odd, this is for the even. We substitute the formula of the even with I is equal to 0. We get sine pos and sine pos over 100. Then for the odd, which are 1 and 3, we substitute the values of I of 0 and 1. We get cosine pos and cosine pos over 100. And finally, here are your 4 positions, 0, 1, 2, and 3. You substitute the pos here. You get your 4 vectors. You put them like in a matrix. We call it PE matrix. Then you originally have calculated x. And finally, you add x to the positional encoding matrix. And that's it for the positional encoding. And here, I have a visualization of how positional encoding works. So let's say you want to represent it over dimension, a certain dimension. This is the sine, this is the cosine. So you're basically representing it over like a series of sine and cosine functions. Again, we can simply just add the position and it should work. However, in the original paper, they found that the best way is to use sine and cosine to do positional encoding. And this is a graph of how you do it. Since our model contains no recurrence and no convolution, we should inject information about relative position of the tokens. The tokens are the words. And we do it using positional encoding of pos 2i is sine pos over 10,000 2i over d model, and cosine. Okay? So now we can look actually at the architecture and actually understand it. So we made it. So let's take a look at the architecture, overall picture. So first, we have an input over here. So we have our input sentence. We do input embedding. So what I just explained. So we look up a dictionary, we inject it to a fully connected neural network, and then we get our X matrix of size. Let's say we had n words and D model, and D model is around 512, as I explained earlier in the original paper. Then we add positional encoding, so sine and cosine, like I just said. So we add the PE matrix, 2x, and they have the same size. And here we have our input to the transformer. Okay. Now we made it here. Here we have a vector x, which is x plus positional encoding. Okay. So it has contextual information about the vocabulary from x plus a position of every word in the sentence from the PE matrix. We do multi-headed attention that I explained earlier. And we have a skip connection over here. And the skip connection is used I explained it in different videos, so I'm not gonna go over it here, but it's used to make the model converge faster because we have gradient descent. We have a very long, so check out my UNet video, the end of my UNet video, but you have a very long neural network. You want it to converge faster, so you add a skip connection. So they add a skip connection over here, and basically it's, so let's say your neural network is f of x. You add the original x to it, and this will make the network actually converge faster. And then they normalize, and normalization is better in the case of neural networks because it's better to subtract the mean and divide by the standard deviation. And then they have a fully connected feed-forward neural network, and they do add and normalize again. So basically, they have the input x bar. So they have x bar, which is x plus positional embedding. You get key, query, and value h times. So you get key 1, query 1, v1, key 2, query 2, v2. And in the original paper, they do it 8 times. So they get key 8, query 8, and v8. And using these 8 key, query, and value, they get output 1 till output 8. Then they concatenate them. So here we have our output of self-attention. And after we do the multi-headed attention, we add the skip connection. So we re-add x bar, okay? And then we inject it to a fully connected neural network, let's say f of x. So we do f of the output 1 till output 8 plus the skip connection. And then we add another skip connection again. So we add O1 till O8 plus x bar, just to make the network converge faster. And here we have the output of the first part of the transformer. Now, the first part of the transformer is called the encoder. So this is the output of the encoder. So we have x bar, we do multi-headed attention, then we inject it to a fully connected neural network, and we have the output of the encoder. And the encoder basically encodes like the higher level picture of the input paragraph. Now, as you can see, the encoder sneaks in to the second part, which is the decoder, sneaks in its output. Now, for the decoder, it's the same process. So we have our input x bar, we add positional encode. So we originally have x, we add positional encoding, then we do masked multi-headed attention. I'll explain what masked is in a bit. Then we add and normalize. And the second time we do multi-headed attention again. However, the key and query come from the encoder. So from the encoder we get the key and query, and the value comes from the first attention, and we do attention again. And this is called cross attention. So cross attention is when you're doing attention with your key and query from an outsider. So when your key and query are from, you're computing it from your input, you're doing self-attention. However, when you're getting your key and query from the outside, so the encoder is giving its key and query to the decoder, it's called cross-attention. So we do cross-attention, then we add and normalize. We use a feed-forward neural network, we add and normalize, and finally we connect them to a linear network over here. Sorry, I had not a typo, like a small mistake in what I just said. It's actually the key and value come from the encoder, and the query come from the first attention. I just said it's a key and query and the value here. It's actually key and value from the encoder, and the query comes from here. So let me go one more time because it's a bit complicated. So first, we have our input x. What's this? We have our input x, and x again. X is originally a sentence, and we vectorize it using a learnable, fully connected neural network in the process I explained originally. We add the input embedding, and finally we get x bar. And x bar is used here and is used here as well. It's a bit different here. I'll explain in a second. So here we have x bar, okay? We do multi-headed attention, so we get a key, query, and value 8 times. And we get eight different attention matrices doing attention on different parts, like let's say pronouns referring who, the subject, the verb, and the object, blah, blah, blah. So we do it 8 times. And then we concatenate them to get our output matrix O. And then we add and normalize, so we add x bar to O. We pass it by a feed-forward network, so we do f of O plus x bar. Then we add and normalize again, so we add O plus x bar. When I'm saying normalizing, so we're subtracting the mean and dividing by, subtracting, the mean and dividing by standard deviation. And now we take the output here as, so this is the encoder. We take the output of the encoder as the key and the value over here. And then we're doing cross attention. Then here, we take our input x bar, we add positional encoding. We do masked multi-headed attention. I'll explain what masked is in a bit. We add and normalize, and then we have our query here. And the key and the value come from here. We do multi-headed attention. We add and normalize. We use a feed forward. And finally, we have, and this is the output of the decoder. And finally, we do linear layer and then softmax. So for the final part, we have to explain what masked multi-headed So we just need to explain what masked multi-headed attention is. So it differs a bit from the normal attention. So I made a small whiteboard over here. So in attention, you're getting the normal attention in the encoder. You're getting, so you have an input sentence, I am Ali, for example. You're doing attending I to am, I to Ali, and I to itself. Also am to itself, and am to Ali, and Ali to I, Ali to am, and Ali to itself. And then getting your output matrix. So you're computing key value and query and getting your output matrix. In the masked attention, you're not allowed to look ahead in the sentence. So I is not allowed to look at am and at Ali. So it's supposed to just do attention with itself. Am is not allowed to look at Ali. So let's say we have a longer sentence. I am a boy living in I don't know, Paris. Okay. I is supposed to just look at itself. Am is supposed to do attention with I and itself. A is does it with I and am and itself. Boy. So every word is only allowed to look at the past and not at the future. And the ways you do it is you do it as follow. Instead of calculating as query multiplied by key over radical D, you add a matrix M, and M has zeros to everything before you and minus infinity to everything after you. So whatever value you will get, let's say you'll get a value of 2 here, when you add minus infinity, it will remain minus infinity. So let's say you're doing multi-headed attention of two times. So you get your key, your query, your key and value over here. This is the matrix S, because as I said earlier, you compute it as query multiplied by transpose of key over radical D. Then you add M, and M has minus infinity over here, so you'll have minus infinities over here. You calculate the output as A multiplied by V, So you will get zeros over here because of the minus infinity, and that's it. So you get O1, okay, as A multiplied by V, and then you do the same for the second head, and finally you get O2, and finally you concatenate O1 and O2. So simply, masked attention is that you put minus infinity in the matrix M at everything in front of you. So here I took 3 words in the sentence I am Ali, but if you had a way longer sentence, you will just put this is your matrix, this is your diagonal. Everything here should be minus infinity, and here you'll have zeros before, and here you'll have your diagonal. So zeros everywhere and minus infinity on the right side, and yeah, that's it. And this is what differs in the decoder. So the decoder does does masked multi-headed attention. So it's not allowed to look ahead, it just looks at the words before it, and then it uses it as a query with the key and value coming from the encoder. It adds and normalizes, does a feed forward neural network, and softmax at the end. And that's it. I hope you understood the paper. You understood what positional embedding is, what attention is, how the overall architecture. So we do vectorization, we add the positional embedding, we do multi-headed attention, and this is on the encoder level. On the decoder level, we do the same process, however we do attention twice. The first time we do masked attention with the masking every word ahead. We add and normalize, and then we do multi-headed attention with the key and value coming from the encoder, and the query coming from the masked multi-headed attention. We add and normalize, and we do a linear and softmax at the end. Just one more thing, guys, is that all the parameters here are learnable, and during training, so we're calculating the error and updating the weights. After we finish training, we teach it a certain task. So, for example, the task may be to guess if the sentence is positive or negative. For example, I like coding is a positive sentence. I hate coding is a negative sentence. So we teach it this task by the output probabilities over here and the loss function. Then, to teach it a new task, we remove certain weights. For example, we can remove the weights over here and over here. I don't know. Okay, so we remove weights from the last layer. We teach it a new task, and it already familiarized itself with the first task. The weights will change just a little bit, so it learns a new task. For example, the new task may be to predict if it's a feminine or masculine sentence. For example, I am a boy is a masculine sentence. And then we teach it, and we do the same process. We remove some of the weights, and we teach it a new task, for example, filling in the blanks. And yes, that's it. Simply, we teach it one task at a time. We remove weights from the last layer, and we teach it a new task. However, the paper didn't jump into the LLM part and how we can build a large language model. What I just explained is how you can build a large language model. It just explains the transformer architecture, which later inspired. So the same transformer architecture I just explained, it can be done to images and also to videos, which I will dive in future videos. And in the next video, hopefully, I don't know if I'm gonna do it this week or not. I'm gonna make a small GPT model based on this transformer architecture. So basically, we'll be coding this transformer from scratch. Just a small spoiler, that the GPT model is a decoder only, so it doesn't have an encoder. So all this is gone. So we'll be coding this part over here and making it, teaching it a certain task. Stay tuned. If you have any questions, don't hesitate to leave me a comment or to message me on my LinkedIn that you'll find in the description. See you later, guys. Bye.